Hello, today we're going to talk about significant figures. We're going to approach this topic from an honors level chemistry. We're not going to go over every single little rule of significant figures, but enough that it will be applicable to all of the upcoming honors chemistry topics. So let's first start talking about accuracy and precision. When we're talking about accuracy refers to the closeness of a measurement that you take to its true value. So closeness to a true value. Precision refers to how close your measurements are to one another. So closeness of your measurements to one another. So a really common depiction of this is using an archery metaphor or a darts metaphor, where if you have a dartboard or a target and you get a measurement is right in the center of the dartboard, that's the value that we're aiming for, and your measurement was right on target, so it's very accurate. Okay. Now precise refers to when your measurements are very close together. So if you have your target, you can have your measurements or your darts land very close together, but maybe they are not right at the bullseye. This would still be a precise grouping, but not a very accurate grouping. Of course, we want our measurements to be both of those things, precise and accurate. So ideally, you'd get your measurements very close together and very accurate. We can also calculate the percentage error. How far off from the true value are you? And so there's a couple ways you could write the percent error formula. It's usually the absolute value of your actual measurement minus the theoretical measurement all over the theoretical measurement again times 100. And that will give you your percent error. So how far away were you from the theoretical divided by the theoretical, so you can see the closeness there, times 100. You could also write it like this. I've also seen experimental. So what value did you get in your experiment? Minus the accepted value. So like the published value, the accepted by the scientific community value, all over the accepted times 100. And again, these are the same thing. They're just two different ways of describing what you are getting, what you are measuring as actual or experimental versus the published true value, which we would call the theoretical or the accepted value. So let's do an example with a percent error calculation here. A student measures the mass and volume of a substance and calculates its density as 1.40 grams per milliliter. The correct or accepted value of the density is 1.30 grams per milliliter. What is the percentage error? So our experimental, I'm going to abbreviate, minus the accepted absolute value all over the accepted times 100. That's our equation there. So our experimental was 1.40. The true value, the accepted value, was 1.30. We're going to take the absolute value of that all over the accepted value again, times 100. So when you subtract, you get 0.1, and you divide by 1.3, then multiply by 100, and we get that the percent error is 7.69%. So that's how far off we were from the true value. Okay, so please be careful with the difference here between error and uncertainty. They're two different things. Error has to do with what we were just talking about, where you're comparing your measurements or your calculated values, your experimental values, to the theoretical or accepted true value. So that would be error. It typically would have to do with your experimental setup, issues with the design of your experiment, etc. Uncertainty, on the other hand, has to do with the precision of your measurement tools. Okay, so uncertainty is typically going to be for analog tools plus or minus 1/2 of the smallest increments on your tool. All right, so let's say we've got a graduated cylinder, okay, and we have a line every milliliter. So let's say that's 10 milliliters, and at the bottom, this is the bottom of our graduated cylinder, that's 0 milliliters. So I have a line for every 1 milliliter. Our uncertainty would be plus or minus 1/2 of a milliliter. And so that's how you would record the uncertainty. Sometimes measurement tools will have an uncertainty like recorded on them, which is nice. Some digital tools will have a very specific uncertainty value, but this gives us an idea that like if it's in here, right, that's between two lines. We don't know that very accurately. We can go, up to a 1/2 milliliter above or a 1/2 milliliter below until we get to that line. And so this is what we call the uncertainty for the measurement. And we're going to explore how we can use uncertainty through chemistry in something called significant figures. Now, when we're dealing with chemistry, we're talking about significant figures. So that's which numbers in our measurements are the significant, the important ones. And we're going to define that as all of the numbers, all of the digits that we know for sure, plus one digit that we estimate. Okay, so let's talk about how we measure that using an analog tool. Whenever you have something that has increments like that graduated cylinder that we were looking at before. So let's say we've got our graduated cylinder and there's a line for every 1 milliliter. So that's 10 milliliters and I have a line for every 1. Let's say our liquid that we're measuring is right here. Okay, so we know for sure that, let's say 1, 2, 3, 4, 5, 6. We know that it's between 6 and 7 milliliters. So we know for sure it's 6 point something. We know that. We can estimate one further digit. So let's say maybe it's 6.6. Or you could say 6.5, 6.4. I can't say 6.65 because that would be too many digits. I can't estimate that far. We can only estimate one digit. Okay. All the digits that we know plus one digit that we estimate. And so this would have two significant digits, 2 digits, because we know one and we estimated one. Okay. And this would be true for any analog tool where you have increments, all the ones you know, plus one that you estimate. Let's say, for example, we have a digital tool. So let's say it's like a balance. Here's my very rough estimation of what a balance looks like. And we have our object here, okay? And we're weighing it on this balance. I'm not an artist, but let's say that the display tells us it's, 1.53 grams. The tool that is measuring is doing some of that estimating for us. So we can say that we know for sure it's 1.5. Those are the digits that we know. And it is estimating the 3 for us. So it still counts as a significant digit. It's just doing the estimating portion for us. So this one would have 3 significant figures. I'm going to abbreviate significant figure as sig fig, just for simplicity. And this one is 2 sig figs. Okay, so now there's a couple of rules we're going to talk about for how to count significant figures in measurements. Especially if you don't have the tool in front of you, it will make it much easier for you to understand how to count those sig figs. All non-zero digits will count. So anything that's not 0, 1 through 9, you definitely count them. Zeros between numbers always count. So if I have something like 1003, those zeros are between two other digits, so they count. And we've already said that all non-zero digits count. So the 1 and the 3, those count. This one has 4 sig figs. Zeros at the front of a measurement never count. So if I write like 00304, even if there's a decimal there as a 0 at the front, they never count. Or if my decimal is here, it still doesn't count. They don't count. So only these three that would be 3 sig figs. And finally, zeros at the end of a measurement only count when there is a decimal. And the decimal can be anywhere in the number. So let's say I've got 0.00310. There is a decimal, so this 0 at the end counts. So all 3 of those at the end there count. The zeros at the front do not. This one would have 3 sig figs. Now if I don't have a decimal, let's say I have 1010 is my measurement. There's no decimal there. It's just a comma to denote place. So 0 in between counts, non-zero digits count, but this 0 does not count because it's at the end and there's no decimal. So that one's 3 sig figs. Let's do a few more examples. So for A, all non-zero digits count. So all 3 of these count. That's 3 significant figures. For B, non-zero digits count. Zeros at the end count when there is a decimal. There is a decimal. It's right there at the end. So that makes the 0 count. So this one has 4 sig figs. For C, non-zero digits count. The 0 at the end only counts when there's a decimal. There's no decimal there, so that 0 at the end does not count. This one only has 2 sig figs. Non-zero digits count. Zeros in the middle count. Zeros at the front of our measurement never count. So those 2 zeros at the front don't count. There are 4 sig figs. And the last one for E, non-zero digits count. Zeros at the front never count. Zeros at the end only count when there is a decimal. There is a decimal. So these ones count. So this one has 5 sig figs. You might also be asked to round numbers to different amounts of significant figures. Let's practice this using an example. Let's say I have 154,235. Now this measurement has 6 sig figs as it's written. Okay. Let's say I want to round it to 5 sig figs. I'd count 5 significant figures and look at the next number. If it's 5 or higher, it makes it round up. If it's less than 5, it rounds down, and you would replace that last digit with a 0. As it is, since it's a 5, I'm going to round up. I would have 240 now. So the 35 rounds up to a 40. And this would have 5 sig figs. 1, 2, 3, 4, 5. That 0 at the end is not significant because there's no decimal place. What if I round it to 4 sig figs? 1, 2, 3, 4. Look at the next digit. It's less than 5. So I'm going to round down. So now I'm just at 200. I'm just going to fill in zeros as placeholders, so I still know the size of the measurement. But now I only have 4 sig figs because the zeros at the end are not significant. I could round to 3 sig figs. Look at the next digit, it rounds down. The zeros become placeholders. I could round to 2 sig figs. That rounds down. Or I could round to 1 sig fig. The next number is a 5. That 5 causes it to round up. It's going to round to 200,000 with just 1 sig fig. None of those zeros at the end are significant. So that's how you would round based on the number of significant figures you need for a particular scenario. Now the last section here is using significant figures for mathematical operations. And our first set of rules comes when we're adding or subtracting two numbers. When we're adding or subtracting, you round to the least number of decimal places. So let's say I want to add 1.52 plus 1.034. And I would need to find the sum of those two things for whatever's going on. I'm first going to add them. I get to 2.554. And then I can need to check where do I round. So this one has 2 decimal places. This one has 3 decimal places. You always pick whichever one's the smaller number of decimal places. And that's how many decimal places need to be in your answer. So I go 1, 2 decimal places, and you look at the next digit. If it's 5 or higher, you round up. If it's less than 5, you round down. And so you basically lose the 4 in this case because it's less than 5. So 2.55. And so that one has 2 decimal places, just like the least number in my problem. And you can follow that same set of rules whether you're adding or subtracting. Now, when we're multiplying or dividing, we follow a different set of rules. If we need to multiply or divide two measurements, we need to round our answer to the least number of significant figures. I'm going to abbreviate as sig figs. So let's say we've got one of our measurements is 3.003, and I want to multiply by another measurement, it was 0.21. The first thing you want to do is multiply. Actually, plug this in, multiply out. I got 0.63063. But where should I round that answer? Well, our first measurement here, that one has 4 sig figs. Non-zero digits count, zeros in the middle count, that's 4 sig figs. My second measurement here has 2 sig figs. Non-zero digits count, the 0 at the front never counts. So you need to pick whichever one's smaller. I have 2 is smaller, so my answer needs to have 2 significant figures. Zeros at the front don't count. So I go to the first 2 that are significant, look at the next digit. If it's 5 or higher, you round up. If it's less than 5, you round down. So that 0, it's less than 5, I'm going to round down, so my answer is just 0.63. I still need the 0 to show how small the number is, but it's not significant. So my answer has 2 sig figs, same as the smallest number of sig figs. Let's do 2 more examples with this. If I am subtracting here, okay, first thing I want to do is actually subtract those 2 values. I got 2.8297 when I subtract. If you're adding or subtracting, you have to round your answer to the smallest number of decimal places. There are 2 decimal places here, and this one has 4 decimal places. So you need to pick whichever one's smaller, so 2, so my answer needs 2 decimal places. You look at the next one. If it's 5 or higher, you round up. So this becomes 2.83. The 2 rounds to 3 because of that 9. And so my answer has 2 decimal places, just like my smallest number of decimal places. For B, since we're multiplying here, same rules for multiplying or dividing. The first thing I want to do is actually multiply these 2 values. I got 37.968. And when you multiply or divide, you need to use sig figs. Our first measurement here has 2 sig figs. My second measurement has 4 sig figs. Whichever one's smaller is how many sig figs should be in your answer. So you go 1, 2 sig figs. You look at the next digit. If it's 5 or higher, you round up. So the 7 rounds to an 8. So I would round this measurement to 38 as my answer. There's 2 sig figs there. And so that is my final answer for that one.